Hi, in this video, we want to take a look at geostatistical simulation. All right, so we're going to be working through example code from Applied Spatial Data Analysis with R, Chapter 8, Interpolation and Geostatistics. Here are the authors of the textbook. Here is the book's website, and you can download this for free as a PDF through UCF's website if you are a student. All right, so let's get to it. All right, so in geostatistical simulation, what we're going to do is I want to see a realization of the situation that could lead to the data I have. All right, so I've observed data. What I'm going to do, I'm going to try and come up with some way, some shape, some form that of what could be happening to give me exactly what I observed. All right. Now, what we're going to do is we're going to do this a lot of times. We're going to do a large number of simulations when we do this. Why do we do that? Well, there are infinitely many possible ways that I could ultimately get the data that I'm observing. So what we're going to do, we're going to do this repeatedly over and over and over to get an idea of what is kind of like a central tendency and average of all the simulations, and that'll give me more insight into what potentially could be going on. So remember, if I'm doing data science, I don't actually know what's going on. If I knew what was going on, I wouldn't be using data science. So here, what we're doing is we're basically trying to fill in the gaps of information that we don't have otherwise. Now, simulation honestly is an inefficient way of tackling these types of problems because we have to do so many simulations, so over and over and over, so many iterations, so many runs to get like a reasonably good idea of what's going on. But this is a powerful tool for us to solve a lot of problems that we can't tackle otherwise. All right, so the author of the textbook says that there are two types of simulation for this purpose. There's conditional simulations and unconditional simulations. Conditional simulations provide realizations that are like true to the data that we observe. So everything that I observe in the simulation results 100% jives with what I observe. Unconditional simulations, what they do is they just take the averages and the variability and then work from there. So if I have measurement error or something like that, I can try and average that out. All right, so the GStat package only handles one type of simulation. This is called sequential simulation. And we have several different models for tackling this. So whenever I do a simulation of this form, I have to have a mathematical model that I'm assuming is correct. Most frequently, most of the time, we're going to assume a Gaussian distribution, the classic bell curve. And when I say bell curve, that's at the locations of interest as I work through this. We can use Gaussian for our mathematical model that fills in the gaps. We use indicators, and multivariable is possible also. Now, the type of information I can get out of this for the GStat package is for trends and for like the block mean values. All right, so how is this actually executed? Well, sequential means really what we're going to do, we're going to create a path through all of the points that are in our data set for our locations. Since we're doing geospatial simulations, what we're going to do, we're going to create a path going through all the measured locations. And along that path, we're going to take the first location. We're going to compute the conditional distribution given the data and previous simulated values. We're going to draw a value from the conditional distribution. Then we're going to add that value to the data set. And then we go to the next unvisited location and then repeat. So along the path is I walk up to the location. I use the information I have to get a distribution. I randomly simulate a value from that distribution, and I add that to my data set as if it was original true data. And then I go to the next location, repeat over and over and over. All right, so when I draw the value, this is probably going to be a Gaussian or an indicator Kriging estimates. Now, the Kriging estimates will frequently give us values between 0 and 1, so it won't truly be an indicator value, but we could round off or take that to be the probability of the 1 for the indicator, something like that. We could look at it that way. Now, this process can take a very long time if I'm using all the data points I have. So it is good practices. If I have enough data, what I'm going to do, I'm going to limit the number of points used for computing the distribution using the Nmax parameter. And that will speed things up considerably. This first step of computing the conditional distribution is the one that's going to take the most time. Now, something that we can do if we want to, we can actually set up what our coefficients are beforehand, and this will give the function less work to do, and I can make sure I get the coefficients I want if a priori I know what they should be. All right, so let's go ahead and let's do this 6 times just so that we can get a feel for what's going on. So in this, I'm using the Kriging function, which is nice that this jives so well with the predictive modeling and model diagnostics. Here's my formula. Here are the locations that I have my observations at. Here are the locations I want to have modeled in the simulation. Here's the model that I believe to be correct. Here is the number of times I'm going to run a simulation. And then here in Max is the number of data points I use to estimate a particular point used, points on the ground. All right, and so let's take a look at what we get. Here, I'm just going to go ahead and print the output of the simulation using the SP packages spplot function. All right, and we can see that these are all pretty similar, but there are differences between them. Each of these are distinct. If I kept on running over and over and over, I would get distinct values for each of these. And so I can look through, and when I see like kind of an average of all the simulations at a given location, that gives me an idea of what's going on. Also, I get a distribution of the values, so I have a more complete representation of what's going on. Now, by doing this, I am using theoretical belief about what's going on at that location to fill the gaps on what's going on. If my model, if my conditional distribution is poorly selected on my part, I will get simulation values that will be crap compared to reality. And frequently we won't know until it's too late that we have a bad, run of simulations. All right, so let's go ahead and take a look at nonlinear spatial aggregation and block averages. So block averages, what we can do is I can just take a region and average over the entire region if that's more consistent with what I want. One thing that this will do for us, this will reduce the variance and the standard error at the location that overall, and it will be a more stable, more reliable estimate. Unfortunately, it's a coarser look at what's going on, so I will also have some information loss. So we have to, for our project, decide what's best to do. All right, so let's go ahead and set up what the area that we're interested in. Here, we can see are the coordinates. And these are, we're going to set this up as an 18 by 2. So what's going on is that these 18 coordinates, see 1, 2, 3, 4, down to here. These 18 are the first coordinates of the location, and these 18 are the second coordinates of each location. And so this coordinate here corresponds to this coordinate here. They're paired together. Remember, R wants to put things in by columns instead of by rows. So it's a little bit different than how a lot of people would do it. Now I'm going to pass that. Those coordinates are in here to define the polygon, which I put in the polygons aspect. If I had multiple polygons, I could put them in here as a list. And then I put it into a spatial polygons object from the SP package. That way I can work with it using all the power of the SP package. Now, what I'm going to do is I want to create a spatial pixel data frame of the simulation area, then run simulations to find information about what we're interested in. All right, so how I'm going to do this, you notice that here are the coordinates I'm passing. I'm passing that into the grid that we have, and now that is my new spatial pixels data frame. Now, once I have that, I'm going to drop that in as a new area. So this is the region that I want information about. I'm using the Krieg function to build a model using this formula, this data set, and this model to get information over this area here. What we're going to do, we're going to do 1,000 simulations. And I'm only going to use 40 points for each location just to make sure that things don't get too computationally heavy. Now, what I want to do is, for this situation, for this problem that the author proposes, what I'm really interested in is, at this location, is the zinc measurement above or below a certain cutoff? And so here, what we're going to do, you notice I've got the cutoff here. I want greater than the cutoff is what I'm interested in. And remember, the modeled value is on the log scale. So I have the cutoff inside log. And then I'm taking an average. And I'm using the apply function to go over each of the simulations. This margin 2 tells me it's over the columns, and boom, I get all these values. So here I can see this gives me a like the fraction above 500. So we can see that most of the time, about 65 to 75% of them are above 500. All right. And then I can take an average over a region to get the to estimate the likelihood that the mean of the target variable is above a cutoff. And here, so when I get the predicted value off of this kriging, so I'm just dropping this in, dropping the spatial polygons area in there. This is a polygon, so it's going to average out over the entire region. I get predicted value. And if I want to know the probability that a normal distribution will be above this, it's like 0.99 was the actual value. I suppressed a lot of the digits for printing to make it easier to read as we look through all the stuff. But it's 0.99, 0.98, something like that. It's a pretty large number. So let's go ahead and visualize the cutoff simulation output. So here I'm setting up that I want to have 2 subplots. I'm using the layout function to do this. I want to be, so when I change aspects of the parameters of the visualizations, I want to be able to go back to where it was before. I want to be able to get back to defaults. And so this is just saving that so I can get back to it later. So now I'm changing the margins to be 0 on all 4 sides. So here, this is a vector of 0, 0, 0, 0. The first 0 is for bottom, then second one is for left, third one is for top, and the fourth one is for the right. And so now what that means is I'm using the full area of my plotting region to make it easier to see. So let's go ahead and plot use grid part A. And here, this is just going to be a solid gray all over. And then I'm going to put a line around the area that we've been working over. And then I'm going to put the histogram over it. So here, this is the area that we're actually interested in. Here is our simulation values for that area. And this gray region is for the entire possible region that we could be studying. So for some reason, this is more interesting to us than the rest of the sample region. And now I return my plotting margins to what they were. Now, If I just wanted averages over certain regions to do block averages, I could do that by specifying the block argument in the Krig function. All right, so now let's take a look at multivariable and indicator simulations. All right, so what we're going to do, we're going to focus on indicator target variables. So we think of this as a binary target, but it's handled a little bit differently here. All right, so here we have all the possible soil values for our measured locations, and we see 1, 2, and 3 are the possible values. Okay, well, what I could do, since this is categorical, I could work with models that I'm interested in the probability of 1, that would be a model, or I'm interested in the probability of 2, that would be a model, or the probability of 3. And so if I was interested in modeling these, I could make 3 different models total for all of these. All right, so to model this, what we're going to do, we're going to use the fit variogram function. I'm going to specify the VGM function for me. So here is the sill. Remember, that is the vertical amount. Range is the horizontal amount, and nugget is that vertical bump, while models tells us the mathematical format of it. Now for the variogram, I just specify what is the formula. So we're not using any covariates, we're only using location. And here is my data that I'm going to build a model on. All right, so now how I use this, I take the variogram that I've fit right here, I pass it into the Krig model. Notice I have the same formula. I'm using same data. And now here's the data that I want to do the simulation on. So here are the locations I'm actually interested in for having my inference. Here we're just doing 6 simulations. In reality, I would do 1,000, 10, probably about 10,000 if it's computationally feasible. Here I'm specifying that I am using indicators, and I'm specifying that I only want 40 locations used in modeling each point. And now let's go ahead and visualize what we get using, once again, SPplot from the SP package. And since I'm doing a indicator model, I'm just going to go ahead and go full red, or I'll just use 2 colors, just showing that this is to indicate when I believe, the model believes that soil would be equal to 1. So whenever it's red, we're saying soil equals 1 from the modeled value. And we can see, like down at this southwest region, highly likely that soil is going to be equal to 1 according to the simulation, and then also along the riverbank along here, and then less likely in the rest. All right, well, that's all I've got for you. Take care and goodbye.